Okay. All right, two categories of physical properties that we talked about yesterday. Again, I don't remember how far we got. Some classes got further than others. So we'll start with this. Two categories of physical properties. What's one? Good. Intensive property. And the other one? Extensive. And what's the difference between intensive and extensive? Let's look. All right. So you didn't study last night. Okay. You're talking about a 2x4?
Yeah, we only talked about like.
Right. Well, give me that then. I mean, it.
No matter what size of the substance, it'll still. Well, I thought no matter what size substances, it'll still flow because that's the same density.
Okay. So an intensive property means that it doesn't matter how much of a substance you have, the property stays the same. Don't say it though, okay? The property stays the same. So it doesn't matter if you have 1 drop of water or 5 gallons of water. It doesn't matter if you have 1 sliver of wood or a 2x4 of wood. So it doesn't matter the amount of substance that we have, the property stays the same. An example that we used was 2x4. What property were we looking at, Aubrey? We're going to pay attention here. So the property we were looking at was density, if I can spell it right. Okay. And then you're saying that we didn't get to the extensive one? No. Did we talk about pizza yesterday? We didn't. Oh my goodness. Okay. Okay. So intensive property then is again, a property that doesn't matter how much you have. It always stays the same. That's the key. It always stays the same. Okay. There is a little twist to it today, though. Extensive property. How many of you like to munch when you study? What do you munch on? Cookies. All right. I would do that too. Chips, carrots, grapes, apple slices. Oh, you said you munch one? Cheez-Its?
Oh, yeah.
That's a good one. Yep. Popcorn. My daughter's all about popcorn. Okay. We tend to.
Chips, cheese. I drink water.
And water. So, remember in biology, maybe if you had Mr. Jordan, that you burned some food?
Yeah.
Remember why you burned food? Well, that would be one reason. No one remembers the why you burned the food besides seeing if it catches on fire? Dog food was a good one. Cheetos usually is a good one when they burn. Peanuts, that's a good one when they burn. Nope. Yeah, you don't remember why you did that? Just because you just wanted to burn food? You didn't talk about calories in food? Remember that? That's why you did the lab. Remember that?
Yeah, I did.
Now it comes back to a little bit. Okay, so a calorie is food energy. So when you eat food, like a Chips Ahoy crack or a cookie, is that? Okay, so when you eat food, it has energy in it, and so when you eat it, it's the energy in your body is called a calorie. Okay, some of you might be on a 2,000 calorie diet. Some of you may not even count calories because you eat whatever you want because you're young and metabolism's high. Some of us oldies have to kind of pay attention to that unless you're active. So food contains calories, contains energy. Okay, calories is an energy counter. How many of you like pizza? Pizza place. What's your favorite pizza place, Ben? Give me your top 2. Wow. Okay, give me top 5. Top 5. First one come to your mind. Jets. All right. Pizza Ranch. Okay. Hungry Howie's. They got the flavored crust. You have a certain crust you like?
Butter Parmesan.
Butter Parmesan. I haven't had that. I'll have to try that. Other places you guys like? What's that? Domino's. Okay. DJ's. DJ's kind of a favorite local town. Okay. All right. Marco's. Yeah. So how many of you could eat easily one slice of pizza? One slice. How about 2 slices? You go 2? You go 3? 4? Wow. 5?
I can eat a whole pizza.
6? Okay. You may eat a whole pizza. A whole pizza is usually 8 slices. Yeah? Hungry. Just enjoying the food. Take a while. Okay. So how many out here? If I eat 1 slice of pizza, would you agree that it has a certain number of calories in it? Okay, quite a bit of calories. And would you agree that it has a certain amount of energy? Okay. Now, if I ate 5 pieces or 5 slices of pizza, would it have the same amount of calories?
Pizza still does, but
So 1 slice versus 5 slices. Would it have the same amount of calories? No. Okay, so my amount changes, right? 1 piece of 5, my amount changes. What else changed? I'm just stretching. What else changed? The calories and or energy. Okay, energy. That is an example of an extensor property. Just the opposite of the intensor property. An extensor property, it does depend on the amount of substance. And energy is the answer you want to have for that. Okay? So for an extensor property, it's a property that does depend on the amount of substance. Okay? And the example was energy. The more food you have, the more mass you have, the more energy you have. So it's going to change. Energy is the answer you want to have for that. Other examples, it's kind of cheesy, but would be mass. The more mass I have, the more mass I have. And volume would be another one. The more volume I have, the more volume I have. That's kind of cheesy. So I'd rather for you to use energy as your answer on the test, okay? Extensor property. It does depend upon the amount that you have. The more you have, the more energy you have. More mass of pizza, more slices, more energy. All right, what is the formula for density? We didn't get this far yesterday? No, it's in your packet, if you have your packet handy. All right, so density equals mass divided by volume. Okay. And if I were to ask you to derive a formula for mass or derive a formula for volume, do you understand what I mean by the word derive? Where did it come from? You're going to take this equation. I want you to rearrange it and solve for m. I want you to take this equation and rearrange it and solve for v. Okay, just like you did back in math class, back in Algebra 1b probably it was. Okay, all right. So what is the formula for mass? If I asked you to find mass by itself, m by itself, what would it look like? Okay, density times volume. And then if I asked you to find volume by itself, what would it be? What is it? Mass times density? I have two yeses. Megan, you're saying, I don't know. Ooh, discrepancy. Who's right?
Actually, I'm done with the. Do I drain all that hot gross water on the side?
Oh yeah, when you do that, it'd be a good idea. Yep.
you multiply like a v on each side to get rid of it on one, and then you have mass equals density times volume, and then you divide by the density on each side.
So mass over density for that. That one kids usually miss. I don't know why, but for some that's a tough one. So whenever we give you an equation in class, you are responsible to solve for any of the variables in that equation. You learn that in math class. Okay, so that's what you need to carry over with you from math class. If it's a struggle with you, find someone math savvy can help you, or see me after school sometime. We're going to work on that too. Okay, but this is expected coming into class. It's a requirement that you pass Algebra 1A, 1B. Okay. Now, Common units for density. It's mass over volume. Most common units would be grams over milliliters. Again, this is on your packet of notes. Grams over milliliters. You're going to see that a lot. You'll also see grams per centimeters cubed. You see that a lot. So those are the two most common ones that you see in class. If you look on your packet of notes, it gives you some other ones that are fair game. So any mass measurement and any volume measurement. So it could be kilograms per liter. It could be grams per liter. All right, you have mix and match any type of units in there, but these are the two most common. Okay. This one we've been working on using sig figs in our calculations, and this comment is very important. So not only do you want to write it down, but I also want to highlight it because I will keep you accountable to this to make sure we do our math in a proper way. So it says that we do not use constants for signification. Okay? Do you understand what I mean by a constant? Like, anybody know what the speed of light in physics? No one knows the speed of light. Okay, it's kind of fast. How about, what is it, Corinne?
2.998 times 10 to the 8.
Oh, it's on the sheet. Nice.
If you count everyone, take it.
Rock, there you go. 2.998 times 10 to the 8 meters per second. That's pretty fast. That's 7 times around the Earth in 1 second. It's kind of quick. Okay? But that's a constant. That value never changes. Okay? So a constant means that's a value that doesn't change. Right? Density doesn't change for a substance. Okay? So when we do our math, we do not use constants for our signification. I kind of coined this word. So in other words, when you do math and the answer has to use proper sig figs, we don't use that constant value for that sig fig part. Okay? So let's do an example. Let's say that we have density given to us, and it's going to be 0.89. Go ahead and write this down and work on it. Grams per centimeters cubed. And let's say that we have a volume of 6.321 centimeters cubed. And I want to know what the mass is going to be. Okay, so I'm giving you a couple of variables there. Go ahead and calculate it out. Apply your sig figs that we talked about. Yeah, that's fine. That at the table is fine. I'll get it. Perfect. Thank you. Yep. Rock. There you go. Hi, girl. Representing. Well, you get 5% bonus points per test. So they took the first test, and some did well, some didn't. They can use 5%. If they did the summer assignment, they have 5% they can add to the test on any test. Yeah, you can say, hey, I want 2% on this test, I want 1% on this test. You can break it up any way you want it.
Oh, but you only get top 5.
5% for the whole trimester.
Oh, okay.
Yep. So it's a good deal. All right. What's that? I treat it like it's a college class. I treat it like a college class. So we do homework. You don't do it, big deal. But you come to a quiz or test, it's all on you. So if you don't do the work, you're not going to do well in the homework. But I don't ding you for not doing the homework.
Forgot my textbooks.
Like 20 pounds of weight right there for you.
I'm like, I feel like I'm supposed to be carrying.
All right, so we have density and we have our volume, so we're just going to quickly do a little multiplication, and we get 5.62569 centimeters cubed on the calculator. And for my correct answer, what would I have? Based on what we just talked about, what would be the correct answer? $5.6. Everybody agree with 5.6? 5.6. Grams, everybody agree? So centimeters are going to cross cancel. And mass is measured in grams, so that's a good way to check. Good. Everybody agree with 5.6? Based on what we just talked about, 5.6 is the answer. You think it's 5.63? I did. So density is a constant value, correct? We just established that. This is a constant value. So this does not become sig figable when we do sig figs in the answer. I coined that word too. What's that? So we'd have to have 4 sig figs in the answer, because we only have 2 values that we have to look at. This is a measurement, this is a constant value to us, okay? We only use measurements for sig figs. Okay? This is a measurement, this is not a measurement. This is something that is constant, something that's given to us, okay? Yes?
So how are we supposed to distinguish, like, what is a constant and what isn't? Because I guess most of us didn't know about
Anytime you have a derived, well, I just told you up here it was a constant,
the density.
right? Because we said extensive, intensive property density never changes. That means it's constant, doesn't change.
Like for other,
And then if you look at the units, whenever you have a derived unit, most of the time it's a constant value. Okay? Most of the time it's a constant value. If you have a derived unit means that you have 2 units. So see how this is 1 unit?
So it's not derived.
Right. So this one has 1 unit, this one has 2 units, has grams per centimeters cubed. So measurements are usually just 1 unit. If you have something that's not 1 unit, that's usually a giveaway that it's a constant. Or you can always ask. Or the problem usually says what values are constant to. So something in that problem should indicate that. Okay? So the answer here then would be 4 sig figs. So we would have 5.626. Yeah, very good. Okay. And then the last question, what is meant by direct or inverse relationships? This will segue into our graphing today. What is meant by direct or inverse relationships? You thinking, Elena? Anything come to mind?
Like if they're both going up, or if one goes up, one goes down.
Okay, which is which, you remember?
Direct, both inverse, or like opposite.
Okay, good, I'll take that. So if it's inversely related, they're opposite. One goes up, one goes down. Okay? And if they're directly related, if one goes up, the other goes up. Or if one goes down, the other goes down. You can do both, I guess. Okay, on your packet, at the top of page 3, whoop. At the top of page 3, it says that temperature is or density is temperature dependent. See that line at the top? You want to highlight that. Density is temperature dependent. So again, this is the only time it really kind of changes. So it's constant at a certain temperature. So the density of a substance at a certain temperature, right? So it's how compact they are. Yeah. It's how compact they are, how closely the particles are connected to each other. It's how dense they are, okay? So in our example here, my molecules are really close to each other, so it has a certain density to it at a certain temperature. But when I heat the substance up, what happens to my molecules? They spread out. They get more energy. They vibrate more. They break away from each other, and then they spread out. So the density here is less or greater than the density here. The density here is less or greater than the density here. Less. So this is less dense. So what's the connection between temperature and density?
The hotter, the less dense it is.
Okay, so if I increase temperature, I decrease density. And vice versa. Okay, if I increase temperature, I decrease density. Now, on your handout, you have this table of some common substances. We got gold, mercury, lead, aluminum, corn syrup, water. You need to highlight water. I'd like for you to know the constant density of water at room temperature. So this says at 20 degrees Celsius, and so we just call it room temperature. Okay. So on your test, if it says that room temperature, what's the density of water, you're going to say 1.00 grams per centimeter cubed or grams per milliliter. That's fine. Do not put 1. We never have 1 for sig fig. 1 is a very, very poor measurement. Okay? So we have more than one digit for our answer. So you're going to put 1.00 for your answer for that on the test. Also on this, I want you to add zinc. Okay, on the column there. So someplace on the column, add zinc metal. And 7.140. 7.140. Zinc. Now, one of the cool things about density is that we can use density to identify an unknown substance. Okay, we can identify an unknown substance knowing its density. So the substance can be a solid. It can be solid or liquid or solution. So I have these blocks up here. This is a white block. This looks like a plastic block, but I don't know really what it is yet. And then I have an unknown green solution. It'd be kind of cool to know what that stuff is. Can I drink it? Is it poison? Have somebody else drink it? Are they going to die? Have my neighbor's cat drink it? Are they going to die? You know, are they going to hawk out and get really buff and stuff? So we can identify substances knowing what their density is. So that being said, what two variables do we need to calculate a substance's density? Volume and mass, okay? So when you get into a lab Monday on your inquiry labs, you keep that in mind. Okay, keep that in mind. What do you need to calculate density, okay? So underneath that chart, there is a problem I want you to work on. We have a student who has this block of silver metal, and they think it's going to be zinc. Read through that problem and figure out if they are correct and why or why not. All right, go ahead and work on that. Well, application. So in the problem, we're given mass, which is one of the variables that we need. We're given dimensions of the block, okay, length times width times height, dimension of the block. So the length times width times height gives us the volume. And we get 3.3929 centimeters cubed. One thing you also need to be aware of is we don't do any rounding during this because this is not our answer. Okay, we don't round until the end. This is what we call an intermediate step. Okay, so the rule of thumb is we usually keep one or two extra digits with this as we move over to here. Now, if you keep this on a calculator, you can write down 3.39 on your math book if you want to, but on your calculator, you can use it for the answer, the previous answer, right? If you do that, then you're fine. If you don't, then your answer is going to be off. Okay, so just kind of keep that in mind, that this is not, we don't do any rounding. We lose the significance of this measurement or this calculation if we start rounding. But this is, since this is not our answer, we have to wait until we get to our answer before we start to do the rounding stuff. That being said, is the block zinc? No. What is it? It's aluminum. Okay, very good. You just identified her block of metal. Okay, easy peasy. Easy peasy. Okay, do the next one underneath of it. Now we have a liquid. Reason through this one though. This was a lot of data in this question, so weed out what's important, what's not important. And as you do that, I'll pass out the graphing stuff here. Liking the shades, Kelly. Sorry, Heather. Okay, check your answers with a neighbor. Talk to me. When other Aubrey gets back, gotta go potty too. All right, so on the problem, they give you a lot of information. Okay, they give you a lot of information. We need the mass of the liquid and the volume of the liquid. Read through the problem. They give us the volume of the liquid. But they give us a bunch of other masses. They give you the mass of the graduate cylinder. They give you the mass of the graduate cylinder plus the liquid. Okay? So this is the mass of the graduated cylinder. This is the mass of the graduated cylinder plus the liquid. Okay? So if I subtract the two, now I have the mass of the liquid. Right? You might need to do that on Monday's lab. When you do the math, you get 1.370 grams per milliliter. Make sure you use the right sig figs. Okay? And what is the substance? Corn syrup. So it doesn't matter if it's a solid or if it's a liquid, you can figure out what the density is and we can identify it. If it's a solid, if I were to give you one of these blocks, how would you find out the density of one of these blocks? Yeah, you have to take the measurement of the length and the width and the height to find the volume, and then you mass it.
What is that?
I don't know. Number 19. We have a, actually number 20. 19 or 20, probably the same. We have an answer key in the back. We have a bunch of these blocks that we sometimes use it with. I'm going to use the liquids with you guys this year. Yeah. It was like plexiglass or some sort. Or some sort of acrylic. This feels like it's balsa wood or something, very light.
Yeah.
Okay. All right. All right. So, are you okay with the using density for calculations? Yeah. You have the equation. All you're doing is plug and chug and solve for unknowns. Basic algebra. Again, plug and chug. Again, if you need some work, 91 through 93, that part of your textbook, work on those problems. I'll give you answer keys. Email me. I'll send you answer keys. Whatever I got to do for it. Okay, but you got to put the work into it. Right? Again, I made copies of your book, so if you want a copy of that throughout this hour, you can grab one of those. Now let's transfer gears into graphing. So on the handout I just gave you is R74 through R77. So a lot of times when we do data in lab, we like to graph the data, and you're going to do this on Monday. You're going to graph some data. It's going to be the same thing that's going to be on your test. Okay, so it's the same thing, but you got to have that experience with it. So we have x and y axes. What variable goes on the y-axis? On the y-axis, dependent. Must be the other one. Okay. Now on your handout, I underlined independent and dependent. Your book used a different term, manipulated and response. Don't worry about that. We're going to use the words independent and dependent. Okay. So this variable depends on what this variable is. What's this variable called? It's the independent. So whenever this is changed, this is affected. That's what you have to understand. So when we start to do our labs, if we want to investigate some phenomena, we want to see what happens when something else is changed. Okay. Now, when you do this, sometimes you have a graph, and maybe we'll do something like this. We get like a line here, and would you say this is a inverse or direct relationship? Inverse or direct? I would say direct. So as my independent variable goes up, my dependent variable goes up, right? What do we call this here? The y-intercept. Very good, the y-intercept. So if my line does not, if my data only gives me this, you can extrapolate that line all the way through until it crosses. So we have the y-intercept. Okay, and what is the y-intercept equation? Slope-intercept form. What's the equation? Y equals mx plus b. Know this equation? What's our b? It's the y-intercept. Okay, so take whatever line you have, you graph it. Wherever it crosses the y-axis, that's the value of b. What's m? M is our slope, okay, which we'll look at in just a second. Y is going to be the value of the dependent variable. X is going to be the value of the independent variable. So if I have, maybe time is my independent variable, and I want to know what y is at a certain time. So in 15 hours, what's the value of y? So maybe y is mass. Okay, maybe y is mass. So I'm doing some reaction. I want to know over a certain amount of time what happens to my mass. Okay, so in 15 hours, I can figure out what mass I have left. Or vice versa. If I have a certain amount of mass left, how long did it take for that to break down? So are you familiar with this? You're familiar with this equation and stuff? You should be. Okay, all right. So here's what I want you to do for slope. If you look on your handout, it tells you that slope equals the change in y over change in x. All right, I would like for you to use your data to calculate slope and not necessarily the graph. So sometimes if you have a graph, they'll say, hey, use the graph, and you can go here and here, or you can go here and here, or maybe here and here. They say find some points and do the rise or run. I want you to look just at the data and make it a lot easier for you. Whenever you have a delta or change in, it's always final minus initial. So I want you to take the final value of y minus the initial value of y. So my final value and my initial value. I want you to take the whole scope, not just a small portion. So in your handout, you have this as an example. Okay, we have the time as the independent variable and the distance as my dependent variable. X same way, xf minus xi, final minus initial. So we're going to have 75 kilometers minus what? My slope, with on your handout. 15. So my final value of y minus my initial value of y. Okay, 75 minus 15. And then for time, we're going to have 7 hours minus 1 hour. I don't want you to just pick two data points. Okay, I want you to use all the data points in there. This will help you for the test, help you for the exam. On the exam, question number 7 has something to do with the graphing. See how I'm giving you a bunch of exam questions along the way here? You'll have about 85% of the questions by the time you get done. All right, if you go ahead and do the math, I think it's 10 kilometers per hour, if I'm not mistaken. You got it figured out? Yeah. Okay, all right. Okay, now I kind of took the line of this example on your handout and I kind of extrapolate down here, and I'm going to call that 5 for my y-intercept. Everybody agree? Yeah. Okay, we'll call it 5. It might be 4, but the way it's drawn, we'll call it 5. So with that in mind, I want you to figure out this question here, question B. It says, how long did it take for a bicyclist to get 40 kilometers from home? So where did he start at? How far away from home was the bicyclist at the start of the trip? 5. Okay. So question B, how long did it take for the bicyclist to get 40 kilometers from home? I want you to figure that out real quick. Might want to use the equation we just came up with. Slope-intercept form. All right, you know the slope, you know the y-intercept, and you know distance.
Okay, wait. Not you.
Again, you got to prove your answer with how you come up with it. You just can't reason through it and give me an answer. You got to be able to support that. Does this help you? Y equals my slope. What's our slope? 10 kilometers per hour. That's my slope. Do I have X? What's my intercept? 5 kilometers. Okay. So the question says, how long did it take for the bicyclist to get 40 kilometers from home? What is 40 kilometers? Is it time or is it distance? Distance. So isn't that your Y? Okay, so 40 kilometers go here. What are we trying to find? We're trying to find time, trying to find X. So does that help you now how to use that equation? You found slope, you found the slope-intercept. Y is your distance, X is your time. Now go through and do the math. How long did it take him to go 40 kilometers? 3.5 hours. 3.5 hours. Yeah, on this one you need to show the work. If it doesn't say show the work, then yeah, I can do it too. Yes and no. Now I'm going to give you a big push here for your lab on Monday. So you want to pay very close attention. I'm going to give you some big hints here. Okay, on your packet, if you turn the page to the last page, at the top, you have some data. You're going to graph the data, and you're going to do A, B, and C. Number 1, A, B, and C. Okay, get that done pretty quick. You're going to graph that, answer the questions. Then you're going to go down number 4. Number 4, then you're going to do all of number 4. Number 4 is similar to your tests, similar to what you're going to do Monday, and similar to the exam. Okay, so number 4 is a big one. Yes, if you need more, I can give you more. I would do one on each side. Yeah, kind of spread out a little bit, easier to use. Okay, got that? Number 1, A, B, and C. Number 4, you're going to do all of them, A through F. Graphing is the key part here. They tell you what's the independent, dependent variable, so that makes it a little easy for you. I'll do the same thing on a test. I'll tell you what variable I want as the independent or dependent. You have to make the graph. Graphs have a title. Graphs have a label on the x-axis and the y-axis with the measurements. Okay, so be very careful when you do that for the homework, also for the quiz or for the test next week. Okay? Now, I'm going to stop here for just a second. I'm going to give you one more thing to think about, and then I'm going to cut you loose with whatever time we have left. Okay? All right, so here's so stop real quick. We're going to transition to Monday. Monday, you and your lab partner need to come in with a procedure ready to go of how you're going to do the following. Okay, it's on your packet of notes I gave you. It says that you need to come up with a method or a way to determine the density of water in a lab setting. You're not going to Google it, whatever. You need to come up with a way to collect data to determine the density of water. Now I'm going to turn that a little bit. Some of you are going to have water. Some of you are going to have unknown liquid. The very last page of that lab packet, you have a bigger table with a bunch of liquids on it. Okay? I'm going to pick one of those liquids, maybe 2 of them for you. You won't know until you come in, so whatever's at your lab station and at your spot, that's what you get. It might be water, it might be whale oil, it might be oil or resin, it could be gasoline, it could be anything. Okay? So your job then, between now and Monday, is to come up with a procedure of how you're going to collect data And then how are you going to determine the density of your substance? Okay? My question to you would be, how many samples do you think would be good to validate your answer? Just one? Would one be okay?
No.
3? Okay. 3 plus? I would say 3 to 5 would be good. Okay, 3 to 5. 10 would be awesome. If you have time, 10 would be awesome. Okay, more the better, right? So remember, what two variables do you need to calculate a substance's density? Volume and mass. So with that in mind, you have the rest of the hour to do either or. You can work on that procedure together, but you need something hard copy-wise come Monday. Do not come in empty-handed or you get 0 for the lab. You're not going to wing it. I need you to come up with a procedure, a plan of attack of how you're going to collect this data. What's your procedure? Okay, it doesn't have to be long, but you need something to go on. Or you can use this time to work on the graphing. No, you can handwrite, it's fine. Okay? All right, so here's what's going to happen. Eyes up here. Here's what's going to happen. Monday, you're going to come in. If you have any specific questions about the graphing, we will talk about those first. If not, you're going to have those out on the table. I'm going to check and see that they're done, and then you're going to work on your lab. It shouldn't take you more than 20 minutes. One's fine. Yeah, one copy per group is fine, so you can Google Doc each other. Then you're going to hold on to that data, and then after the test on Tuesday, we're going to come back to your data, and I'll have you graph everything. Okay, that's kind of the plan. Now, one thing I didn't take into account is the next hour. So if next hour is a wash where we don't have a 4th hour, then to your advantage, it might be bumped where you might have an extra day and we'll have the test on Wednesday. Okay, so that might work to your advantage that way. Okay? All right, rest of the time is yours. Be productive.